The solar system. We need to go beyond our stellar neighborhood. But rather than wait for humanity to ascend beyond the confines of our solar system and become a space-faring civilization, astronomers at NANOG have used a clever trick. You may recall our recent episode on pulsars and how we discussed that these ultra-dense neutron stars are able to spin with remarkable stability. They emit light along their poles, and we can detect the pulses that we receive as those vast beams of light swoop around and hit the Earth again and again. These pulses come with such precise certainty that they are used as clocks of the cosmos, able to keep time across vast distances. Therefore, we can use already identified pulsars to supply us with reliable signals from thousands of light years away. The pulsars are like the mirrors at the end of the LIGO arms, but rather than sending us back a signal we send across, they are generating their own. Nanograph have cleverly concocted an imaginary interferometer that stretches for thousands of light years. And all we need to use it are the good old radio telescopes that we've been using for decades. But our calculations will only be as good as our observations. When choosing pulsars to observe, we need to make sure that they are suitable for the task. The best candidates are hand-picked and added to a group called a pulsar timing array. For Nanograph, they have made use of 68 pulsars, which were chosen for the following special properties. They had to be spread all across the sky, so we can figure out how these massive gravitational waves are affecting space-time in all directions. Also, they had to be millisecond pulsars, which means they complete millions of rotations per second. In our recent pulsar video, we talked about how these fast-spinning pulsars are expected to be the most stable and dependable when it comes to the regularity of their pulses. In fact, their stability even rivals that of some atomic clocks. We could not ask for better timekeepers to be dotted across space and time. This regularity means that we can take measurements of the time their pulses arrive and continue taking these measurements over multiple years to see if there are any changes happening. Of course, the times of arrival can vary due to all sorts of factors such as the change in distance between the Earth and the pulsar, as both objects continue moving around space. But we can take this into account quite easily. However, there are less predictable factors such as random fluctuations in the interstellar gas the light is traveling through, causing delays that aren't coming from the stretching of space-time. How do we get rid of the random noise in our data from pulsars located thousands of light years away? With statistics, we can isolate the gravitational wave background from the random noise by considering correlations between pairs of pulsars in the pulsar timing array. Just like LIGO, one tunnel isn't sufficient. We need two pulsars on each end of our imaginary tunnels. If similar fluctuations show up with two pulsars, it is unlikely that the random noise aligned in such a way to make it appear by chance that they are acting in unison. It is far more likely that there is a common cause underlying both those fluctuations, such as the possibility that the photons from the two pulsars are riding the same gravitational wave that are washing by them both. We can then relate these correlations of pulsar pairs with the angular distance in the sky. If there is no gravitational wave background, we expect there to be no correlation and the graph to show a straight line at zero. However, if the data shows a special curve called a Heelings and Downs curve that would indicate that a gravitational wave background is responsible for the variances. That's what Nanograph have succeeded in doing. On the 28th of June 2023, based on over 15 years of continuous observations of their 68 pulsars, they announced strong evidence for the gravitational wave background. This is the graph we've been waiting for. This is a hallmark of gravitational waves which stretch along one direction and squish in the perpendicular direction. This is exactly what we are seeing with this graph. When pulsars are separated at right angles, their photons are experiencing an opposing effect as they travel to Earth. The error bars in the data appear quite large, but the researchers have calculated that the data shows that the existence of a gravitational wave background is statistically significant at the 3 sigma level. This means that there's only a 1 in 1,000 chance that this is a false alarm, and that this data was the result of mere chance. In physics, the 5 sigma level is considered the gold standard for a discovery, but 3 sigma is still very strong evidence. As they collect and analyze more data, astronomers will be able to reduce those error bars and finally announce an official discovery. So, what secrets does this gravitational wave background reveal? While we cannot pick apart the sources of the collective noise just yet, we hope that these techniques will eventually allow us to listen in to specific supermassive black hole binaries and figure out what the signal can tell us about the creation of the universe. Until then, astronomers will continue to use their galaxy-sized detector to calculate how we are bobbing up and down in the turbulent sea of space. Have you heard about nanograph before? What secrets do you think gravitational waves could reveal? Let us know in the comments below. Every year since 2018, astronomers have spotted a mysterious blue flash in the sky. It is one of the brightest phenomena in the universe. An explosion that makes the average supernova look like a faintly lit candle in the distance. Some have been spotted closer to us and others billions of light years away. They look similar enough to one another, but no one knows what they are or what causes them. Through rigorous observation and analysis, astronomers began decoding a pattern and formulating